Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Imagine standing on a windswept coast. Waves crash against jagged rocks, and the tide rolls in and out with a rhythm that is repeated for millions of years. It's powerful, mesmerizing, and seemingly unstoppable. Yet despite all that energy moving past us every day, we rarely stop to think, what if we could capture it? The ocean covers more than 70% of our planet, and with every surge and ebb, it carries enormous energy. Wind and solar panels grab headlines for renewable power, but the tides, predictable, relentless, and incredibly dense, offer a type of energy that we can forecast with near-perfect accuracy. Unlike wind, which can die down at any moment, or sunlight, which disappears at night, the tides are as reliable as Moon's orbit itself. That's where tidal stream turbines come in. These underwater machines are essentially wind turbines submerged in fast-moving water. As tidal currents sweep past, they spin blades connected to generators, producing electricity. It sounds simple, but the engineering behind it is extraordinary. And while a few large-scale projects are now proving that the concept works, we're just scratching the surface of what's possible. Hi, I'm Drew, and in this episode, we're diving beneath the waves to explore the physics, the engineering, and the promise of tidal stream turbines, the ocean's hidden power plant. From the forces that move the water to the turbines that capture it, we'll uncover how humanity is beginning to tap into a clean, predictable, and virtually untapped source of energy. By the end, you might never look at the tide the same way again. Our world runs on energy, and as populations grow and industries expand, the demand keeps rising. At the same time, climate change is forcing us to rethink how we generate power. Fossil fuels are no longer a long-term option, and while wind and solar have made huge strides, they come with limitations. Wind doesn't always blow, and the sun doesn't shine at night. Energy storage helps, but it can only go so far. Now imagine a storage of power that's predictable, dense, and global. The ocean carries that promise. Every wave, every current, every tidal surge contains massive amounts of energy. Yet despite this enormous potential, the ocean's energy has remained largely untapped. For decades, engineers experimented with tidal barrages, which function like small dams and other wave harnessing devices. Some of these projects worked, but they were costly, complex, and often had environmental drawbacks. The sheer scale of the ocean, the corrosive salt water, and the unpredictability of certain wave patterns made large-scale energy capture difficult. This is where tidal stream turbines change the game. Instead of trying to stop or store the water, these turbines capture the motion of the water itself, converting kinetic energy directly into electricity. They're smaller, less intrusive, and take advantage of the fact that water moves predictably with the tides. Where tidal currents are strong enough, these machines can generate electricity year-round, day after day, and with far fewer interruptions than wind or solar farms. But harnessing this energy isn't as simple as dropping a propeller into the sea. There's physics to master, engineering challenges to overcome, and environmental impacts to consider. In the next section, we'll dive beneath the surface to see exactly how the ocean's motion can be transformed into a hidden power plant, starting with the physics that makes it all possible. So how exactly do tidal stream turbines capture energy from the ocean? To understand that, we need to start with the tides themselves. Tides are caused primarily by the gravitational pull of the moon and sun, combined with the rotation of the Earth. As the moon's gravity pulls on the ocean, water bulges toward it, creating a high tide. On the opposite side of the Earth, the inertia pulls the water, producing another high tide. Low tides occur in the spaces between these bulges. This cycle repeats roughly every 12.5 hours, and because the moon's orbit is predictable, we can forecast tides with astonishing accuracy, even centuries into the future. But tides aren't just about water rising and falling. They also create fast-moving currents, especially in narrow channels, bays, or between islands. And these tidal currents are the rivers in the ocean that the tidal stream turbines tap into. Unlike wind or sunlight, which can vary minute by minute, tidal currents are incredibly reliable, making them ideal for steady power generation. Now let's talk about energy in motion. Water is about 800 times denser than air. That means even a relatively slow-moving tidal current carries a huge amount of kinetic energy, especially when compared to wind energy. For example, a 2 meter per second tidal flow carries roughly the same energy as a 16 meter per second wind. This density is why underwater turbines can produce significant power without enormous structures. The turbine itself is essentially a giant underwater rotor with blades designed like airplane wings. As the water flows, the wings spin, but the design is delicate, and if the blades spin too fast, they can reduce efficiency. Too slow, and they don't capture enough energy. Engineers use something called the tip-speed ratio, the relationship between blade tip speed and water flow speed, to optimize energy extraction. Now that we understand the physics behind tides and tidal currents, let's dive into the machines that actually capture this energy. Tidal stream turbines themselves. At their core, a tidal stream turbine has four main components: blades, a rotor, a generator, and an anchoring system. The blades are shaped like airplane wings or wind turbine blades, and as tidal currents flow past, they exert lift and drag on the blades, causing them to rotate. That rotation turns the rotor, which is connecting to a generator that converts the rotational kinetic energy of the blades into electricity. From there, the electricity travels through subsea cables to the shore, feeding directly into the power grid. There are two primary types of tidal stream turbines: fixed bottom and floating. Fixed bottom turbines are anchored directly to the seabed, usually in shallow or moderately deep water. Engineers must carefully account for how the seafloor affects current flow. Currents near the bottom are slower due to friction, but they're also more powerful, which influences blade design and placement. Floating turbines, on the other hand, are tethered to the seabed but can move slightly with the current. This introduces new engineering challenges. The system has to handle not only the spinning blades, but also the motion of the platform itself. Dynamic modeling is crucial for predicting forces on the turbine and ensuring it operates efficiently and safely for years in the water. Beyond placement, engineers faced other challenges. The ocean is an unforgiving environment. Salt water corrodes metal parts, barnacles and algae can attach to blades, and storms can produce extreme currents. Material science plays a huge role here. Blades are often made from advanced composites to resist corrosion while remaining lightweight and strong. Generators must be sealed against water intrusion, and maintenance access is carefully planned because working underwater is expensive and complex. Some designs even feature modular or retractable components, allowing engineers to pull turbines above the waterline for inspection or storm protection. Others use hydraulic or direct drive systems to convert rotation to electricity efficiently, minimizing mechanical losses and minimizing inspection. Ultimately, tidal stream turbines are elegant examples of applied physics and mechanical engineering. They take predictable ocean motion, translate it into mechanical rotation, and then into clean electricity. They may sit quietly under the waves, but each turbine is a mini power plant, harnessing one of the nature's most consistent and powerful forces. Tidal energy has fascinated engineers and scientists for centuries, but capturing it efficiently has always been a challenge. Early experiments in the 70s and 80s focused mainly on tidal barrages, small dams built across estuaries. These had to control the rise and fall of water to make electricity, but they were expensive, disruptive, and limited to certain geographic regions. The idea of tidal stream turbines, machines that could harness the moving water itself rather than holding it back, was floated around the same time. However, at that point, materials, engineering knowledge, and underwater cabling technology weren't ready. Prototypes in the 80s and 90s offered proof of concept, but suffered from durability issues, corrosion, and inefficiencies. Most projects stalled before reaching full-scale operation. It wasn't until the 2000s and 2010s that tidal stream turbines began to emerge as a viable solution. Advances in composite materials, corrosion-resistant coatings, and subsea cabling, along with knowledge gains from offshore wind farms, made it possible to build turbines that could withstand the harsh marine environment. Designers also learned how to optimize blade shapes, rotor sizes, and generator systems for maximum efficiency in dense water currents. The breakthrough isn't that the turbines work, it's that we now understand how to scale, maintain, and integrate them into energy grids. They're no longer just experiments, they're a glimpse of a future where predictable tidal energy could be a major contributor to clean energy worldwide. Even though tidal stream turbines are a breakthrough in renewable energy, they're far from perfect. There are several hurdles that have kept them from being widely deployed, and understanding these challenges helps explain why the technology is still emerging. First, there's the economics. Installing turbines in the ocean is expensive. Anchoring systems, subsea cables, and specialized vessels for installation all cost far more than building on land. Maintenance is even trickier. Engineers can't just send a crew truck to the site. Every repair or inspection involves boats, divers, or remotely operated vehicles. These factors contribute to make the cost per megawatt higher than most mature technologies like wind or solar. Then, there's durability. The ocean is an unforgiving environment. Saltwater corrodes metal parts and barnacles. Algae and other marine organisms can attach to the blades, slowing rotation and reducing efficiency. Storms and other extreme currents put enormous mechanical stress on turbines, requiring materials that are strong yet lightweight. Engineers have made huge strides with composite materials and corrosion-resistant coatings, but the harsh reality of the marine environment means wear and tear is inevitable. Environmental concerns are also significant. Turbines must be designed to avoid harming fish, marine mammals, or seabed ecosystems. Sediment flow can be altered by turbine arrays, which may affect habitats downstream. Modern projects monitor these impacts closely, but it's a constant balance between generating energy and protecting the environment. Finally, there's grid integration. Many of the best tidal sites are far more offshore or in remote regions. Transmitting electricity efficiency to urban centers requires high-voltage subsea cables, which are expensive and technically challenging to install and maintain. All these challenges add up, which is why tidal turbines are still underused. They're powerful, predictable, and technically feasible, but the combination of cost, maintenance, environmental concerns, and the engineering complexity they demand has slowed large-scale adoption. Yet, each project provides valuable lessons. Every failure and every success redefines designs, reduces costs, and brings us closer to a future where tidal energy can be a reliable part of our renewable energy mix. In other words, the ocean's hidden power plant is already here. Just needs time, innovation, and some smart engineers to reach its full potential. Now that we've seen how tidal streams work and the technology evolved, let's take a closer look at where they're actually being deployed today. These projects both show the promise and the challenges of harnessing ocean for the energy. The Maygen project in Scotland is the flagship example. Situating in the Pentland Firth, a channel with some of the fastest tidal currents in the world, Maygen launched its first turbines in 2017. Today, it consists of multiple turbines, generating enough electricity to power thousands of homes. The project has proved individual insights into turbine durability, maintenance schedules, and energy output forecasting. Engineers learned how to manage seabed anchoring, prevent biofouling, and optimize blade performance in strong, turbulent currents. Maygen is still expanding, showing how a single site can grow from proof of concept to a significant contributor to the local energy grid. Across the Atlantic, Canada's Bay of Fundy has long been recognized for its enormous tidal range. Several experimental tidal designs have been installed there to test new designs and materials. The extreme currents provide a natural laboratory for understanding how turbines handle varying flow speeds, sediment load, and seasonal changes. Some turbines even have been fitted with sensors to monitor marine life, ensuring that energy protection doesn't harm the environment. In France, pilot tidal stream farms have been used to test innovative turbine designs, from blade shapes to floating platforms. These sites allow engineers to experiment with direct drive generators and modular systems that can be lifted for maintenance or storm protection. Lessons learned in France are feeding into global design improvements, helping engineers build turbines that are both efficient and resilient. South Korea is another country investing heavily in tidal stream energy. Projects along its northwestern coast have deployed multiple large-scale turbines, feeding electricity into the national grid. These installations highlight changes with cabling, grid integration, and maintenance logistics. They also demonstrate the scalability of tidal turbines when managed correctly. All of these projects, a few trends stand out. First, turbine placement is critical. Locations with strong, consistent currents gain far more energy than slower sites. Second, maintenance and durability remain key concerns. Underwater environments are harsh, and even the best materials need careful monitoring. Third, while each project is smaller than a conventional wind or solar farm, they offer predictable, reliable energy that complements other renewable sources. These real-world projects are not more than experiments. They are more than experiments. They're proving that tidal stream turbines can move from pilot stages to full-scale power generation. And with each new deployment, engineers refine designs, reduce costs, and get even closer to tapping the ocean's full potential. Beyond the engineering marvels themselves, the people behind tidal stream projects play a huge role in making them work. Teams of marine engineers, environmental scientists, and local communities collaborate to ensure turbines are not only efficient, but also responsible stewards of the ocean. Researchers dive beneath the waves to inspect blades, monitor seabed conditions, and study how marine life interacts with the rotating turbines. Sensors track fish, crabs, and other species, helping teams adjust placement or blade speed to minimize disruption. Communities near these projects are often involved too, providing feedback on noise, shipping navigation, and aesthetics. One engineer described standing on a small boat, watching currents swirl around a turbine with a feeling of raw power of the ocean firsthand. An experience that made the potential of these machines feel almost alive. These human stories remind us that tidal energy isn't just about technology, it's about people working with nature to unlock a cleaner future. Looking ahead, the potential of tidal stream turbines is enormous. Imagine hybrid offshore energy platforms that combine tidal, wind, and wave power on a single site. These platforms could generate electricity almost continuously, using the sun, the wind, and the tides together to smooth out fluctuations in supply. Advances in materials science will also play a critical role. Engineers are experimenting with self-healing composites and stronger coatings that resist corrosion and biofouling. These innovations could drastically reduce maintenance costs and extend turbine lifespans, making tidal energy far more competitive with other renewables. We might also see modular and mobile turbine designs. Imagine turbines that can be lifted above the water for maintenance or repositioned to optimize power capture and changing currents. Floating turbines could adapt to seasonal variations in water flow, maximizing output year-round. Scaled effectively, tidal stream turbines could reliably power entire coastal cities, complementing wind and solar to create a resilient, renewable energy grid. Unlike solar and wind, which are intermittent, tidal energy is predictable. This predictability makes it an incredibly valuable resource for utilities, helping to stabilize electricity supply and reduce dependence on fossil fuels. Ultimately, the vision is a world where the ocean itself becomes a hidden, massive, and renewable power plant, quietly feeding electricity into homes and industries without polluting the air. Each tidal turbine deployed is a step toward that reality, showing that the combination of physics, engineering, and innovation can turn the motion of the seas into something tangible, useful, and transformative. The figure is not about imagining its potential, it's about engineering, scaling, and integrating these machines so that the tides flowed for millions of years can finally work for us. Let's return to that windswept coast we imagined at the start. Waves crash, tides roll in and out, and beneath the surface, enormous forces are quietly in motion. For centuries, humanity has watched this power and wondered how to harness it. Today, tidal stream turbines offer a glimpse of the answer, a way to turn the predictable motion of the ocean into electricity that could light our homes, power our industries, and help combat climate change. These turbines are more than just machines. They're applied physics in action. They take the dense, powerful currents of the sea, spin massive rotors, and convert kinetic energy into clean, reliable electricity. From the early experiments of the 70s to the modern utility-scale farms in Scotland, Canada, and beyond, we've learned how to design, maintain, and scale these systems. And while challenges remain, each project brings us closer to unlocking the ocean's full potential. This breakthrough isn't just technical, it's conceptual. For the first time, we have a technology that can predictably harness ocean currents on a meaningful scale. And yet we are only beginning to scratch the surface. The tides flow every day, ceaseless and unstoppable, waiting for us to tap into them responsibly and effectively. So the next time you stand on the shore, watch the tide rise and fall, and think of a hidden power beneath the waves. Each surge of water is more than a rhythm of nature. It's a potential power plant, quietly moving, patiently waiting, and ready to help build a cleaner, more sustainable future. Tidal turbines may still be emerging, but their story is already one of innovation, persistence, and promise. The ocean's hidden power plant is here, and it's just getting started.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.